Okay, thank you, Jared. Hello, everyone. So today I'm going to talk about my thesis, which is, as Jared said, risk assessment including damage accumulation due to earthquake sequences. Before I start, I would like to say that this presentation is made with the help of my supervisor, Paolo Bazzurro, who is here, but also with the help of my colleagues, Mosen Korangi, Thanasis Papadopoulos, and Pablo Garcia. So the idea for today is to Okay, so for the idea for today is to have three parts of this presentation. The first part will not be technical. I will talk about what is the motivation behind my thesis, and I will say a couple of words about the traditional seismic hazard and risk models. Then I will move to a little bit more technical part. I will talk about the hazard and how can we model seismic sequences. And I will show you how to use IUSS model for case study Central Italy. And then we will move to the last part, which has to do with the fragility and deriving damage-dependent fragility curves. So first, I would like to say a couple of words about traditional seismic hazard and risk models. Basically, all of the traditional models are based on the main shock only view of seismicity, which means that all of the events that are noted as dependent events are removed from seismic catalogs. And this process is called the declustering. So as an example, I'm showing here the map of Italy and events that happened in the last 40 years. And I'm showing as an example three sequences, one in 2009, where we had almost 300 dependent events, 7 of which had magnitude larger than 5. Then the sequence in 2012, where we also have almost 300 dependent events, 6 of which have magnitude larger than 5. And the sequence is 2016, where we had almost 1,300 dependent events, 9 of which have magnitude larger than 5. After declustering, all of these dependent events are removed, and we are only left with the main shock events, which you can see in this pink circle. When I say dependent events, I mean what is usually called as foreshocks, so the events that happen before the main shock, aftershocks, events that happen after the main shock, and also triggered events, which are events that did not happen on the same rupture as the main shock, but are triggered with the main shock events. So what is the reasoning behind keeping only main shock events? Why is this what we usually use? First of all, in the design philosophy, engineers would say that if the structure can withstand earthquake that has a certain large magnitude, then for sure it can also withstand the earthquake that has lower magnitude, because in the decluster catalogs we usually keep the events that has the largest magnitude. So this was the intuition behind this. The second reason is mathematical simplicity, because it was shown that when we remove dependent events from the earthquake catalogs and when we are left only with the main shocks, we get the Poissonian distribution. And the Poissonian distribution makes our lives easier in a sense that it's much easier to go, it's straightforward to go from rates to probabilities. And probabilities is something that we prefer when it comes to the communication with the public. The third reason was because we wanted to remove the spatial bias that the non-decluster catalogs can have, where seismic rays can be overestimated in some regions where we've seen historically many sequences, and then underestimated in other regions where these significant clusters were not yet observed. The last reason has to do with catastrophe modeling. So practitioners like to say that even though we use decluster catalog, the vulnerability functions that we are using are based on the actual empirical data that we have, which is collected at the end of the sequence. So in that way, we account for the loss after the entire sequence of events. However, in reality, we usually do not use we don't use the vulnerability functions that are based on the empirical data, but we rather use the vulnerability functions that we analytically derived. And also, even if we use the empirical data, then it does not make sense to use the data collected and at the end of the sequence when we are dealing with the quiet periods when we only have main shock events. Another thing that has to do with CAT modeling and insurance companies is that usually, not always, but in most of the cases, insurance claims treat events that happen in 72 hours as one event, but all of the events that happen after these 72 hours, they treat as dependent events. So this means, for example, for the example of Turkey, we had on 6th of February, we had the main shock event, and after 10 days, we had the aftershock that had 6.7, I think, magnitude. And in insurance world, these would be two separate events, and basically the insurance company would pay twice, even though it's clear that this later event was dependent on the main shock event. So recently, it was shown that these traditional approaches are quite inconservative. So, for example, we have sequences in Christchurch in 2010, then we had a sequence in Central Italy, 2016, and also recently Turkey sequence. So as an example, I'm showing here the sequence that occurred in Central Italy between August and November 2016, where we had three very large events, 6.1, 5.9, and 6.61. After the declustering, we would be left with only one event in this entire sequence, which has the largest magnitude, 6.6. So when it comes to the traditional seismic hazard models, all of these dependent events never happened. So only the largest magnitude event with 6.6 magnitude happened. So why are these traditional approaches unconservative? Why the main shock only representation of hazard might not be sufficient? One of the reasons has to do with the declustering methods. So one of the first methods that appeared was developed by Gardner and Knopf in 1974, and their paper had a really simple question: is the sequence of events that occurred in California when we removed the aftershock, is it Poissonian? And the abstract simply said yes. So this method is to this day applied in several national seismic hazard models, including USGS in USA and also MPS 19 used in Italy. So it's a very simple model and it's still used. But we should have in mind that Gardner and Knopf declustering method was calibrated only for the Southern California sequence, and even though these same parameters are used elsewhere in the world. After this, several other declustering approaches were developed, like link-based Rosenberg, then Zaliapin, then also a little bit more complicated models that are based on the stochastic declustering, such as one from Zhang or Robert from Lenus. And you can clearly see that the fact that we have this many declustering methods imply that there is no right way to decluster the catalogs. And this is because the events do not come in nature with labels main shock, aftershock, foreshocks. So this is something that we decided to do for simplicity. So basically there's no right way to select the declustering method. So as an example, we did a small study where we used the region in Central Italy and the instrumental catalog Horus. It's a homogenized catalog. And we declustered this catalog in different ways using three different methods, the Rosenberg, Gardner and Knopf, and Zaliapin. These are the methods that are most usually used. And here on this figure, I'm showing the magnitude frequency distribution of the full catalog, the dashed line. And in different colors, I'm showing these three methods. And this is basically Gutenberg-Richter law fitted to the data. The first thing that you can observe is that the different declustering methods will give us catalogs that have different number of events. So depending on the choice of the declustering catalog, we will end up with the catalogs that have different number of events, basically. The second thing is that when we keep only the largest magnitude events, we can distort the maximum frequency distribution, which is usually assumed to follow Guterman-Richter law. So we apply Guterman-Richter law because we assume that the events follow the exponential distribution. But when we remove main shock events, it can easily happen that we don't have any more this exponential distribution, and then it's not valid to use the Guterman-Richter law. And this is something that is rarely ever checked. Also, the very reason why we do the declustering is because we want to have the Poissonian distribution. And usually it's not even checked if the decluster catalog is following the Poissonian distribution or not. So for example, in the cases that I'm showing, when we decluster the catalog with the Rosenberg method, we are far from the Poissonian distribution. And also, most of them, I would say almost all declustering methods that we have assume that, so first we identify the clusters, then we assume that the main shock is the event with the largest magnitude in the cluster, but does the largest magnitude necessarily mean the largest intensity? So what I want to say that you can easily imagine a case where we have two earthquakes with the same magnitude and same distance, but that the intensity in one case is much higher than in the other. Another reason, so the first reason why the main shock only representation hazard might not be sufficient are the declustering methods. The second reason has to do with the assessment when we have portfolio of structures. For example, this is relevant for the insurance companies. When you have when we look at the only main shock events, then the spatial footprint is much smaller in some cases than when we have a sequences of events. So for instance, here I'm showing the spatial footprint after the 5.8 main shock events that happened on the 20th of May in 2012. And then 9 days later, an aftershock occurred. And of course, we have a bigger number of buildings that are affected than we had in the main shock only case. The last reason has to do with the fact, you know, how I said that in the initial reason why we used only main shock is because we say if the structure can survive the large magnitude event, that for sure it can survive the event with the lower magnitude. Well, what we did not account for is the fact that when we have a main shock event, our structure gets damaged. So when we have aftershock events, our structure can be more vulnerable to the subsequent events. So basically, our structures are weaker. So for instance, here I'm showing the case for the reinforced concrete frames with infills and for masonry buildings. I think this was the sequence in Italy. And I'm showing the damage after the main shock events. And then I'm showing the damage after the aftershock event, where you can clearly see the accumulation and the progression of damage. So to recap, the reason why the main shock only representation might not be sufficient is because the highest magnitude does not necessarily mean the highest intensity, because different declustering methods can yield very different results, and this is a subjective procedure. Because the final catalog of events might not be Poissonian and also might not be exponentially distributed, and this is what we typically assume. Because the spatial footprint increases when we have an earthquake sequence compared to the main shock only case, and also because already damaged structure are more susceptible to the additional damage. So what can we do? The first models that were developed that wanted to tackle the issue of seismic sequences were actually developed for post-main shock conditions and for building tagging. So this means that people wanted to assess, is it safe to enter a certain building after the main shock event. So based on the damage that building already experienced, and based on the probability that the aftershock occur in next days, they will assign tag to a building, so green, yellow, or red tag. This was later extended by Boyd in 2012 and Iervolino in 2014 and they were identifying independent clusters, and they were calculating the exceedance rate of ground motion intensity level at a specific site due to the all events in the clusters, rather than just due to the main shocks. So this approach is still, I think, used a lot, and it's called sequence-based PSHA. In sequence-based PSHA, we, however, still assume that all of these clusters are independent. The good side is that we can start from the PSHA models that we already have, main shock only based, and then we basically add the additional events around the main shock events that we have. What we are using in my thesis is the IUSS model. IUSS model models the entire sequences and their joint effects, and the total rate of events at a particular point in space and time is calculated as the sum of the background rate and the rate of the offspring events. So basically, we start with the background events, and then these background events are capable of triggering new events. And then these triggered events are again capable of triggering the new events. And this procedure lasts until basically the process dies out. It's like a epidemic. That's why it calls IUSS. It's epidemic type aftershock sequence model. So basically the rate at certain site, a certain time, depends on the history. So this model has memory, and it's equal to the sum of the background rate and the triggered rate. And I will not go into too many details about the math behind the IUSS model, but the triggered rate has three parts. One is the productivity part, so how many events are triggered. Then the temporal part, basically we assign the timestamp to each event, and the spatial part where we define where is this triggered event located. And as you can see, there are many parameters in IUSS model that needs to be estimated. What is important is to remember that in IUSS model, there is no distinction between foreshock, main shock, and aftershock events. So there are no labels. Basically, all of the earthquakes are treated equally. We start from the background events, and then on these background events, we add the triggered events. Also, if there are seismologists here, the background events in this case, it does not mean, as it usually means in seismology, the events that are not associated to any fault. It's basically means the events that are tectonically driven, so they are not caused by the other events. Our goal with IUSS model is to use the IUSS model for a long-term seismic hazard assessment, but IUSS model can be used for other purposes. It can be used for diagnostics. It can be used for short-term forecasting. Also, it can even be used for declustering. The steps that we are following when we're using IUSS model are basically collecting the historical data, then calibrating IUSS model. So basically estimating the parameter that I just showed. And here it's very important to have the data of good quality to be able to obtain robust estimates of IUSS parameters. So it's very important to have a good catalog of events where we have many sequences observed, to have a low completeness magnitude, and so on. After this, we simulate the stochastic catalogs, and we compare these catalogs with the historical seismicity. And here we use Turing style tests. I'm going to show you which test I use to validate our model by comparing the simulated catalogs with the historical seismicity. And lastly, we use the model to estimate the hazard at the site or the site of our interest in a certain time window. So here I'm going to show the case study that we did. We basically defined two regions in Italy, one in the central part, which is this green box, and another one in the south, which is this pink box. And we used the HORS instrumental catalog, which is spanning from 1981 to 2020, and the minimum magnitude of 3. We estimated data's parameters using this gathered data and using the maximum likelihood approach, and we defined data's parameters in both of these regions. We noticed that there are some differences in the parameters, so we got different set of parameters in these two different regions. And our question was, are these differences due to the intrinsic properties of these regions? Perhaps because there is different tectonic environment, or because we have a lack of the observed sequences in some parts of Italy. To validate data's parameters, we simulated 500 stochastic catalogs ranging from 1981 to 2020, because for that is the span of our catalog. So basically, we first simulate the background seismicity, and then we add the trigger seismicity using the calibrated ITAS parameters. And we used the seismological Turing style tests that were proposed by Page from USGS, and we wanted to answer the questions: can synthetic catalogs that we produce by ITAS imitate the behavior that we see in the real catalog of events? And there are several tests that we conducted. I'm showing here some of them. So basically, we compared the magnitude distribution, spatial distribution, seismicity rate, and clustering behavior. And without going into too much details, we showed that there is no statistically significant difference between the synthetic catalogs and the observed seismicity. All of the results that I'm showing here, by the way, are for the region 1, so for the central Italy that we defined. We then wanted to compare our estimate with the historical CPT-15 catalog, which starts from 1000 and goes until 2017 with a minimum magnitude of 6. So we are now looking only at the large magnitude events. And we actually showed that the parameters that are calibrated based on region 1, where we historically observed many sequences, matches the historical data in region 2 better. Which would imply, you can see that here where we compare the maximum, magnitude frequency distribution. You can see that the blue line, which is the parameters calibrated based on region 1, match the empirical data for larger magnitude better than the set of parameters calibrated based on region 2. And this basically implies that the same set of ITAS parameters can likely be used in entire Italy. So if we believe that we observed many sequences in central Italy and we trust our parameters calibrated based on this region, then we can use these set of parameters in other regions also. So after we gain confidence into the parameters that we estimated, we moved to the derivation of the hazard curves. We picked a site in central Italy, Norcia, where historically many sequences have been observed, and we simulated 20,000 one-year-long stochastic catalogs with some initial condition using the inversion method. Basically, for every event in the stochastic catalog, we generate finite rupture planes by using the OpenQuake and using the share area source from 2013, I think. And then we find the intensity at the site of our interest, so in Norcia, for every single event in the stochastic catalog using the GMPs. Before moving to the hazard curves, it's important to note that as ITAS has memory of the events that happen before the time that we are looking at, events that happen before the forecasting period that you can see here in blue can trigger the events inside our forecasting period. And the events from forecasting period can similarly trigger the events outside of the forecasting period. So it's important actually to start with if we want to estimate the hazard curve 1 year from now, it's important to feed the model with the events that happened before this event. How to define the length of the disconditional period? There is no unique way. We show that if we use 2 years, it should be sufficient. So that said, we consider two cases. One case, it's called unconditional case, and the other case is the conditional case. This was actually the method that was initially proposed by Thanasis Papadopoulos. So basically, the unconditional case is something mimicking the random year. We start with the 0 initial conditions, and we sample the 11 years of seismicity. Then we disregard the first 10 years, and we are kept only with the last year. So in that way, we simulate every single time different initial conditions. So in that sense, this is the random year. In second case, which we call the conditional case, we wanted to estimate the hazard in a specific period in time. So we picked the period where we observed the high seismicity, which is in the period from 26 April 2015 to 26 April 2017. That's when the big sequence in central Italy happened. We started with that period, and then we estimated the hazard curve 1 year after that. And I'm showing here the annual rate of exceedance and annual probability of exceedance, and I'm comparing the results obtained with the Poissonian model, so main shock only view of seismicity, and also the IUSS unconditional case and conditional case. And you can show that the hazard rates are elevated when compared with Poissonian model across all of the intensity levels. And you can see also that there is the elevated probability of exceedance when compared with Poissonian models for the higher intensity levels. In the conditional case, we have the elevated probability and rate in basically for all intensity levels. So you can see here with this red line that in conditional case, when we fed our model with the years where we have very active seismicity, we had a very significant, I would say, difference between the IUSS and the Poissonian case. Before moving to so this is basically more or less everything when it comes to the hazard part. Before I move to the fragility part, I would like to say a couple of words about the sequence that happened in Turkey, because I think that this is a good example of why aftershocks can be important. So on February 6th, in 2023, an earthquake with magnitude 7.8 happened in Turkey on the East Anatolian Fault, and it was followed only 11 minutes later by the 6.7 event. And then 9 hours after this event, magnitude 7.6 earthquake happened. Between 6th and 16th of February, we had 1,430 aftershocks, 34 of which had magnitude larger than 5. If we use the standard Gardner-Knopf declustering method that I said is usually used in practice, then we would be left with only one event. So we would be left only with the magnitude 7.8 earthquake, and the damage that happened because of these other events would never be considered. The high magnitude aftershock that we saw in the Turkey sequence is not something new. It's something that was observed also in the past, for example, in Christchurch sequence, and also in the sequence that happened in Japan during the Tohoku earthquake. And even there are some claims that the event that happened in Japan in 2021 that had magnitude 7.6 is actually triggered by the event, by the Tohoku earthquake that happened 10 years before, which had magnitude 9. So as an example, I'm using here the Mori law, which is used in IUSS model as the productivity, in the productivity part. I'm using the Mori model, and I'm using the parameters that were actually calibrated based on the data that we have for Italy. I use this model to see what is the expected number of aftershocks 10 days after the main shock event in Turkey, and I'm comparing it with what was actually observed. And you can see that the match is, of course, not perfect, but it's pretty good. And the aftershock that actually occurred in earthquake are following this exponential distribution that we observed before in the past. So we can now move to the fragility module. When it comes to the fragility module, focus of my thesis is on the older reinforced concrete structure frames with infills that have poor detailing. And I would like to say that there are two parts in the fragility module that are important, in my opinion. One is the numerical modeling, the advanced numerical modeling of structural components. Another one is how to map the damage measure with a specific damage state, and then how to map that damage state with a specific set of repair strategies, and then later with the cost. And even though I believe that the modeling is also very important, because of the time, I will focus only on the mapping of damage measure to the damage state. So EDPs that are most commonly used are drift-based for structural components and acceleration-based for non-structural components. And what we think is that these EDPs may not be able to capture the evaluation of damage in cases when you have seismic sequences, as they are not monolithically increasing. And what I mean by this is that you can imagine that you have your building and that you have a main shock event and you have some maximum interstory drift. And then you have an aftershock event, which has, for example, lower intensity, and you observe exactly, you don't observe a higher drift, but nonetheless, you see additional damage. So this simply means that using drift might not always be a good choice. And studies, there are many studies that were dealing with main shock aftershock analysis, and that they used drift as an EDP. And what they usually conclude is that the progression of damage is noticed only in the cases when the intensity of aftershock is higher than the intensity of the main shock. And in reality, on the field, this is not always the case. So we see the progression of damage, even though the aftershock intensity is lower than the main shock intensity. So that said, we proposed a component-based approach where EDPs are actually monotonically increasing. For this presentation, I'm going to show what we are doing for the reinforced concrete columns that fail in flexure. So I was only focusing here for this presentation on the columns that fail in flexure. We gathered the experimental data. We have 251 rectangular columns failing in flexure. And we started from the modified Parkinang damage index as an EDP. So modified Parkinang damage index has two parts. The first part is based on the displacement, and the second part is based on the energy. And there is the unknown parameter beta that we decided to recalibrate basically using the gather database of experiments. So basically we set the damage index is equal to 1, and then we express beta as you can see here. You can see that we needed to find maximum displacement, yield displacement, and ultimate displacement under monotonic loading for every single specimen that we had in our database. And we calculated dissipated energy by integrating the force displacement curve. So in that way, we got the value of this parameter beta for every single specimen in our database. And we found that the median value of beta is 0.1 and the standard deviation of 0.31 in the estimated damage index. So we were wondering if there is a way to reduce the standard deviation, and we decided to add to the modified Parkinang damage index this additional parameter gamma by fixing the beta value to 0.1 and then again recalibrating the gamma. And we showed that there is, by looking at the data, we showed that there is a correlation between this gamma parameter and the number of cycles after yielding. And you can see this, you can see that on this plot, where we use linear regression to estimate the value of gamma as a function of the number of cycles after yielding. And then using the results of the regression analysis, we calculated the gamma, and then we again calculated the damage index. And we showed that now the standard deviation of damage index is going to be 0.12. So we managed to reduce the standard deviation from 0.31 to 0.12. We then wanted to link this new damage index with the damage states. So we managed to gather data from the literature from 28 experiments where we have a very detailed description of damage, meaning that we know exactly when was the certain damage observed in which time step. And we used 22 out of this 28 experiments to propose the range corresponding to 4 different damage states from slight to the extreme. And then we kept 6 experiments to validate our result. As an example, I'm showing here one of the experiments that we left for validation, where based on the report that we had, we identified the points where we have bar yielding, concrete crushing, spalling, and the steel rupture, which correspond to the damage state 1 to 4. And we calculated this new damage index for every point. And we showed that the values that we obtained here match well the range that we previously proposed. So that simply means that the proposed damage index predicts the damage state well. Okay, so we have the way to model seismic sequences, and we now have, at least for the reinforced concrete columns failing in flexure, we have the EDP that we believe works better when compared to drift. So we can then move to deriving damage-dependent fragility curves. Basically, we start from the intact structure, then we run the analysis. I will show you in which way we can do that. And we get the fragility curves for an intact structure. Then we are left with the damage structure because of the so-called main shock event. And then for this damage structure, we run the analysis again, and we obtain the fragility curves that are dependent on the damage that we observed during the main shock. So we focus on how to find these, how to derive damage-dependent fragilities. And there are different ways in the literature on how we can do this. I would say that the most used way is to use back-to-back IDA. I will not go into the details here, but basically for my master thesis, we did a study where we used reinforced concrete building with infills, and we first excited the intact building with 22 records, which were scaled at 11 intensity levels. Then for every single record, we found the scale factor that correspond to each damage state defined. Then we subjected the building to the damaging, what we call damaging main shock. We follow it with the aftershock record that we randomly chose from the set of 22 records. And we incrementally scale these aftershocks again. And then we repeated this for every single damage state. And in this case, we get, you can see that in this last row, we get damage-dependent fragility curves. The other approach is using the cloud analysis. So basically, we need to define the sequences of the main shock aftershock sequences. The problem here is that we don't have enough real sequences that are observed, so we have to find a way how to populate the areas where we don't have the combinations of the aftershock main shock intensity that we are looking at. And how can we create these sequences? So there are different ways in the literature, from using the main shock event as a main shock and aftershock, or using the main shock ground motion as the aftershock ground motion by scaling it, or producing the aftershock ground motions artificially, and so on. This is not what we use, nor we don't use the cloud analysis, we don't use the IDA, also because there is no basically hazard consistencies. What we propose is a different approach. It's based on the multiple stripe analysis in the conditional spectra, modified to account for the aftershock also. So basically, we first start with the main shock hazard estimation, and we select the ground motions for the intensity level of our interest, as we would do when we use conditional spectrum. And we associate every single record with some magnitude and distance. Then for every main shock record, we simulate realistic sequences of events, and we can do this by using the IUSS model that I explained earlier. So in that way, we sample a certain number of aftershocks, also time since the main shock, location, and magnitude of the aftershock. Using the main shock and aftershock scenarios and using the main shock spectrum, we define the target aftershock spectrum. To do so, we need to have the empirical correlation structure between the aftershock and main shock ground motions, between their spectral coordinates. So we use the correlation structure, which was empirically derived using the seismic sequences that were identified in the IUSS database, and this was done by Thanasis in 2019. And you can see here the correlation between the main shock and aftershock spectral ordinates. And as an example, I'm showing here, so I'm showing here basically the recorded main shock ground motion in this solid orange line, and I'm showing what was predicted by the GMP in this dashed line. So you can see that the recorded main shock is above the GMP mean, which means that using the correlation structure that was derived, that the conditional spectra, aftershock conditional spectra, conditioned on the main shock spectra, will also be above what was predicted with the GMP, so above this dashed blue line. And you can see that the recorded aftershock, which is this blue solid line, actually matches the conditional spectra way better than the mean from the GMP. What this basically means that if we incorporate main shock information, we can improve the prediction of the aftershock response. So basically, to derive the aftershock conditional spectra, we have to know what is the main shock spectrum and also what are the causal parameters of the main shock and aftershock. So once we have the main shock ground motions, we can get the response of our structure for different intensity levels. I'm showing that on this first figure here. And then we can run the aftershock records that we selected to match the main shock consistent conditional spectra, and we get the response after the entire sequence. And you can see that here it's a cloud of points. And as an example, if we want to get, for example, the fragility curve that is dependent on the damage state, that is conditioned on the initial damage state 2 that we observed after the main shock, we will look at the only yellow circles which correspond to the initial damage state 2, and we will look at the yellow circles that are now in damage state 3. So for instance, here I'm showing an example of the damage dependent fragility curves, where you can clearly see that there is a shift towards the left because our structure is more fragile when there is damage already observed. So the more damage we observed in the main shock, the more fragile our structure will be to the subsequent event. So as a conclusion, traditional seismic models consider only main shock events, and this can cause an underestimation both in the hazard and the vulnerability parts. To model the seismic sequences, we can use Data's model, which does not make any difference between the foreshock, aftershock, and main shock earthquakes. We can consider two cases: the random case, where we look at the average year of seismicity, or unconditional case, and the conditional case, where we look at a specific period in time. And the effects of damage accumulation require more engineering work, and it requires smarter choices when it comes to both the modeling and the choice of EDP. And that's it. Thank you.